Welcome back, everyone. I hope you had all refreshing lunch. It was great to see such enthusiasm and participation in session 1 of seminar 149. Let's now continue this engaging journey of learning as we move into session 2 of knowledge sharing session. We have more insights, discussion, and takeaways lined up. So let's start it with again. So I would like to welcome Dr. Lakshmi Paraveswaram for her next lecture. The topic will be design of buildings for wind effects. Uh, Over to you, Lakshmi ma'am. Welcome back.
Thank you very much. I hope you can see my slide.
Yes. You have to just make it full screen.
Yeah, it's full screen only.
Yeah, now it's...
Yes, sir. It is now.
Good afternoon. I welcome you to the third lecture in the webinar 149, Design of Tall Buildings for Wind and Seismic Forces. And this topic is on design of buildings for wind effects. The morning, like we have seen the wind characteristics and how they are affecting the forces on low-rise buildings and how they can be used for the computation of wind effects on low-rise building, especially with respect to the components like walls, roofs, etc. Now, in this session, I'll be focusing more on the structural characteristics and how the wind resistant design of tall buildings can be done. So basically, I'll be focusing on classification of buildings and also the design criteria against wind action and how wind affects buildings of various heights, how to estimate them, and what are the dynamic effects of wind on buildings, and how to estimate this along wind response across wind response as given in IS 875, then aerodynamic interference effects, and apart from this, some aerodynamic design concepts as well. So when we talk about the classification of buildings, like IS 16700, it classifies a building as tall building if the building has a height greater than 50 meter but less than 250 meter, and super tall building is a building having a height greater than 250 meter. And we have in our country buildings with 250 meter or even more than 300 meter tall. Then when we consider the wind action on these buildings, we classify them as rigid building, dynamic, or like a elastic. That the rigid one means like only the static effect of wind on the pressures acting on the various elements, they can be considered. But in the dynamic, the sense that like we will be considering the along wind buffeting forces on the structure. The third category is that there is a fluid structure interaction or wind structure interaction which is taking place, and because of that there are wind effects which needs to be dynamic oscillations which needs to be considered for the design. So Professor A.G. Davenport, he in fact coined this wind load response that how this gust factor method can be used for the design way back in 1960, and still that is being used widely by the structural designers. And you can see that as we saw in the first lecture, that the wind climate that is mainly affected by the terrain and topography, and we have seen that within that atmospheric boundary layer, how the uh, wind speed is changing, and also there is gustiness in the wind, and which is contributing to the turbulence intensity. And then there are eddies which are formed. So those eddies, their size of these eddies, that we represent as the turbulent length. And then these fluctuations, they contain energy. So the spectral density, that is the energy. So wind climate we have seen seen the influence of terrain. Then now how the geometric shape, like both plan, we have seen something about in plan, how they are changing the forces, and then plan, elevation, size. If you recollect, even the force coefficient, that is a function of the plan dimension as well as the height. Then the dynamic properties of structure. When we talk about the dynamic properties of structure, we will be considering here frequency, mode shape, and then the damping. So thank you, Professor Yoginder Singh, giving a similarity between wind and earthquake, and also pointing out the difference between wind and earthquake, because in earthquake, you are considering the time period, but here we consider the frequency of the structure. Then the mode shapes, again, with respect to the frequency, we say that a structure is dynamic to the action of wind, if it has a frequency lower than 1 Hertz. Okay, so that is what we consider. And then the damping of the structure, again, that depends on the material with which that structure has been constructed. Definitely, there is a difference between the damping which we use for wind and earthquake. So about that also I will come little later. So now when we talk about the design criteria against wind action, so any structure we design, we consider the stability, that is the overturning, uplift or sliding. But here basically it is the wind action. So the overturning, that is quite important. Then the sliding also, that is important. Then the strength of the structural components of the building, that is required to have sufficient strength to withstand the imposed loading without failure during the life of the structure. Another important aspect is the serviceability. In fact, about the interstory drift, Professor Yoginder Singh was also telling about that during his lecture in earthquake. So that is also quite important with respect to wind action also. So control of deflection and drift, that they are also important. Why they are important is you have to limit the damage and also cracking of non-structural members. In the case of building, apart from the structural members, you have non-structural members. So to prevent or limit the damage and cracking of the non-structural members such as facade, internal partition, ceiling, etc., that can be controlled with the help of by controlling the deflection and the drift. So that part is also important. So stability, the 3 S which we have to remember is stability, strength, and serviceability. Now, considering the wind action on a building, actually, we need to consider in which direction the wind is going to attack a particular building or the structure. So the forces which are developing in the same direction, we classify them as along wind, forces, and or they are called the drag forces also, and the one which is acting perpendicular to that we call a crosswind forces, or we call them even the lift forces. In some papers and all you will find that, but mostly we use the terminology along wind forces, across wind forces. And as we saw in the morning, like for any structure, when the wind is moving around that particular structure, the pressure distribution around that structure in various phases, they are not symmetrical. And because of that, like it gives rise to a torsional effect. So it will be subjected to, you can say, for the design, like some along wind moment, then like a crosswind moment, some torsional moment. So these things are to be considered for the design when you think about the building design as a whole. Now, there is eddy generation around the building because the approaching wind is not uniform, but it has a lot of fluctuation, lot of eddies which are present, and they are of different sizes. So you can see that the eddy is basically giving the vortices shed on the, you can say this is the upstream side and this is the downstream side, or downwind side, downstream side. In the downstream side, the eddies are generated, and these eddies are like forcing the structure to move in the crosswind direction, basically. That is, if you can see that, like in the morning we saw about the stagnation point, actually where the wind flow velocity is 0, but from this point, basically, like it starts to, you can say separation is happening at this edge, and some reattachment, and then separation again in this edge, and you can see some vortices are shed, and again these vortices are shed. There is a frequency for this vortex shedding also, and when this vortex shedding frequency coincides with this structural frequency, then we say that it is having a vortex excitation or vortex induced oscillation. But what we need to understand is that the velocity distribution in the wall and the velocity distribution after that, they are not the same. Like the pattern is somewhat different. So if you have another object placed here, what will happen that it will be experiencing a different wind flow than the approaching wind flow if this structure was not there. So that means when there are two structures in a separated by a distance, the wind force felt by the first structure and second, they are not the same, because the second structure is in the wake of the first structure. So that also we need to understand. Now, like you can see that this is a rectangular cross section, and you can see that there is a separation here from the edges at A and B, and you can see that it has a very wide wake. Where the flow is separated, there is a wide wake. So you can see that this wide wake indicates that like the drag force or the drag coefficient for this particular structure is on a higher side. But if you see in this case, here this is a rectangular, a square one. And here what has happened is that the flow has separated, but it has reattached. But again, like it has separated from the edges, and there is a shear layer also. And there is a lot of vortices in this particular wake. But you can see that the wake is quite narrow, indicating that the drag force or the along wind force acting will be on the lower side. So that means the plan size or plan shape again and again, I am repeating that with respect to the wind, the shape of the structure, that matters a lot, and also the uh, ratio of the plan dimension, that also matters a lot. Now, coming to another aspect, we said that when a structure is subjected to wind, it is subjected to along wind forces, across wind forces, and a torsion. So, this is the first structure, which is an asymmetric building itself. This is a symmetric building. So, while you are planning, please ensure that the structure is otherwise symmetrical, because otherwise you are making it more vulnerable to damage, especially under the extreme condition. Okay. Now we talk about the fluctuating wind. We have seen these things in the morning. Actually, like this is the atmospheric boundary layer, and the wind has a mean component and a fluctuating component. And what are the forces like because of these fluctuations which are acting on the structures? That is the natural winds turbulence, that the fluctuations in the oncoming wind, that is causing the phenomena called buffeting. Then aeroelastic phenomena, that is, we have a limited amplitude oscillation, which we call the vortex-induced vibration, VIV, and it may be there. It is basically an across wind oscillation. In some cases, like for example, a structure like a bridge, it may be a vertical oscillation and torsional oscillation, but in this case, it will be a crosswind oscillation in the case of building. Then another is the divergent amplitude oscillation, which can cause aeroelastic instability. In fact, if you are designing a bridge, like we don't want this aeroelastic instability to happen. So we want to eliminate the phenomena we call flutter, or the phenomena we call galloping. We don't want that to happen, okay? But this is not the case for the building, but for the building, basically it is the buffeting, and it may be the, another is the vortex-induced vibration, and both these things are of limited amplitude oscillation. But again, this limited amplitude oscillation, we will see that that can cause discomfort to the users. Okay, so there may be some acceleration which may not be that, the user may not be that comfortable. So user comfort is one thing to consider, and with the perspective of the structure being a repetitive action, like even the buffeting, because buffeting will be there in all wind speed, so that can lead to some fatigue. So with respect to the structure, though they are limited amplitude oscillation, it can lead to fatigue, but with respect to the user perspective, like it can lead to discomfort. So that is how, like, one has to consider these dynamic effects on structures, especially the building. Now, moving to the vortex-induced oscillation or vortex shedding, as I said that the vortices are there generated in both phases of this circular structure, and it is going to act, apply forces in both these phases, and the oscillation is likely to happen. So the vortex shedding frequency, basically, that is given by this Strohal number into hourly mean wind speed at height by breadth of the structure. So basically, what we find out is that what is the critical wind speed at which this vortex-induced oscillation is likely to happen. And in general, because we say that we are considering the structures having a frequency lower than 1 Hertz. So in general, what we find is that they happen at a very low wind speed, maybe 10 meter per second or 12 meter per second, means which are much, much lower than the design wind speed. Because if you have a structure like designed located in, say, 47 meter per second zone, but still like the vortex induced oscillation is possible at 10 meter per second or 12 meter per second. Now the question comes like, what is this Strohal number? So the Strohal number, again, that depends on the geometry of the section, and because as I said that for a circular section, it depends on the drag coefficient or even the shading of the vortices. They all are dependent on Reynolds number. So you can see that a value of 0.2 when the D into V is at H is less than 6 meters square per second. Otherwise, it is 0.25. And for rectangular structures, we got the value is around 0.1. Again, these 0.1 or 0.2, they are all determined by the wind tunnel test. Now, there is another interesting point to understand, that like we say that wind is there always, unlike the earthquake, which may be experienced for a particular duration and which may happen once in a while, but wind is there always, okay? But the natural frequency of the structure, that is when the vortex vortex shedding frequency coincides with the natural frequency of the structure, they coincides, then we call it as vortex induced oscillation, and that will happen only at a particular range of wind speed. You can see that here, this is the lock-in region, okay? This flat one, because here like the wind speed is increasing, then there is a lock-in region, then like again the wind speed is increasing, okay? But this vortex induced oscillation will not happen at all wind speed, but it will happen only at a particular lock-in region of the wind speed, which I said that will be lower than the design wind speed, okay? So that is one aspect which we need to understand about the vortex induced oscillation. Now, as per this IS 875 part 3, like they have given tips to understand which are the buildings which are sensitive to wind. One is the fundamental frequency of the structure is less than 1 hertz. Another is aspect ratio, that is height to width is more than 5. So if these two conditions are satisfied, then like that structure is dynamically sensitive. And the quasi-static wind load on this building, like based on the gust factor approach, how to compute that, those things are given. But for doing that estimation, we need to understand what is the frequency of the building. So here the formula has been given how to calculate the time period of the building. So they have given that for moment resistance free without bracing or shear wall resisting the lateral loads, like the time period, that can be worked out as 0.1 into n, where n is the number of stories including basement stories. I'm sure that you are using these formulae for working out. Otherwise, like you can do an analysis and find out what are the time period or the frequency of vibration of the various modes. And which modes are important, that also I said that is the along wind mode, across wind mode, and torsional mode. And basically the modes which are having frequency less than 1 hertz, that is what which are important with respect to the wind action. And for others, like it is based on like the height and the like the base dimension by using the formula T equal to 0.09 H by root D. So these two, like we can work out like the time period, and inverse of the time period, that is nothing but the like the frequency. So we have to work out that the formula is given to work out the time period. From the time period, we can find out, okay, like the frequency. Then we can find out, suppose you know the shape of the building, like rectangular one. So we can find out at what speed the vortex excitation is likely to happen. That is the critical wind speed for the vortex excitation can be worked out. For example, we know the Strohal number and we know the frequency of the structure and the width of the structure. Then the wind speed can be worked out as Fs into P by S. We can work out at which wind speed the vortex excitation is likely to happen. And another important aspect is that the damping of the structure, that is also important. And we know that damping is something which takes out the energy which excites that a particular structure, okay? And every structure that has some inherent damping. But in the case of wind, what happens is that it gives more energy to the system. That is where the divergent amplitude of oscillation, like galloping or the flutter, happens. That is, some negative aerodynamic damping effect is there in such cases. But in some cases, the wind will be having a positive effect on the aerodynamic damping, will be an added damping to the structural damping also. So that means the wind will have both favorable and unfavorable condition with respect to the oscillation of the structure. Now, motion in the direction of the wind, which we call buffeting or along wind oscillation, basically that is because of the fluctuations which are present in the approaching wind. Okay, so the excitation depends on the gust energy available at resonant frequency. Now, the eddies shed from an upstream body may intensify motion in the direction of wind, which may cause the across wind motion. So we now have to understand that the IS 875 part 3, it has given how to first identify whether the structure is dynamically sensitive to wind, and then how to work out the time period, otherwise you can model the structure and work out carry out a free vibration analysis and find out what is the frequency, mode shapes, etc. Anyway, you will be doing that for your earthquake analysis. So a simple way, like you can see that a structure is there and wind load is active, and you can see that the shear force is maximum at the base, bending moment is also maximum at base, and it is also varying. And these are the fundamental modes, like if it is a cantilever structure. So this is the second mode, third mode, and fourth mode. So maybe what you have to consider is the modes which are lower than 1 Hertz. They are interest to you with respect to the wind action. So along wind load, the gust factor method, we said that with gust factor method, we will be using hourly mean wind speed and hourly mean wind pressure. So that we have discussed, and A basically, that is the effective frontal area of the structure, and CFZ is the force coefficient, or you can say if it is the along wind direction, it will be the drag force. Okay. So basically the gust factor is the peak response to the mean response. Now, as I said that Professor Devanpur, when we gave this along wind response computation, like you can see that this is the natural frequency in the x-axis, and this is the spectral density. So this is the background component which we call, and that is because of the energy component in the approaching wind, or the fluctuations in the approaching wind. And there is another peak you can see, that is the response spectra. That is because of the frequency of the structure. that is coinciding with the wind energy, then this peak is happening. So you can see that the gust factor that will be having two components, that is one is a background component and one is a resonant component. Okay, so this we have already discussed, and these things basically the base bending moment, shear, or the variation of bending moment and shear, they are important with respect to the calculation of for the design, how to work out the bending moment, shear force at various levels so that you can size the structure accordingly. Now, like this equation to find out like the gust factor, it has two components. One is the first component inside the square root, that is basically having a factor called BS also, and GV, that is the peak factor of upwind velocity fluctuation. And for terrain category 1 and 2, you can take a value of 3, and 3 and 4. They say that a value of 4 can be taken. And R is nothing but it is twice the turbulence intensity. So what all you need to work out the gust factor is, one is the turbulence intensity, one is the background factor, which indicates the measure of slowly varying component of the fluctuating wind load caused by the lower frequency wind speed variation. And inside this bracket, basically it is not G, basically it is phi. Phi is it is a factor to account for the second order turbulence intensity. So this amendment is also there. So this is the background wind force spectrum, that is the background wind force spectrum, this first component. And second component, if you see, that is basically, it has a called a GR. Here you can see it is a GV component. Here there is a GR component, and then the energy that is represented by E, and beta basically that is the factor which is corresponding, reflecting the, you can say the damping. Okay. So if you see that, like basically GR is nothing but a peak factor for resonant response. Beta is the damping coefficient of the building or structure. Okay. And E is the basically the spectrum of turbulence in the approaching wind speed. And there is a size reduction factor also given. So that those things, when you apply, like you can work out this particular gust factor. And one thing you have to understand that in the equation for calculating the background factor, there is the measure of effective turbulence length scale. Turbulence length scale is nothing but it is the size of the eddies. So there are formulae given with respect to the terrain category, that is 1 to 3, there is one formula and another for terrain category 4. So if you use them, that means you are basically computing the wind force spectrum, that is the background wind force spectrum and the resonance spectrum. So these two, resonance response spectrum, these two are added together to get the value of this gust factor. Now, here, like there are certain structural damping coefficients given here, and it again depends on whether whether it is a steel structure or it is a welded steel structure or bolted steel structure or RCC structure. So the damping coefficient beta which is given is for welded steel structure is 0.01, bolted steel structure is 0.02, and pre-stressed concrete structure it is given as 0.16. Actually, we need to understand here that different damping values are used for seismic and wind analysis. Okay, that is because of the distinct nature of these loads and also the structural response. as I told you earlier, that what are we interested in with respect to wind? It is basically the frequency range which is lower than 1 hertz. That is what we are interested in. Okay. So, but if you consider, say, something like point, say, 2 hertz or 0.25 hertz, okay, then there it becomes 4 seconds. Okay, so the spectrum of earthquake is something different there. Okay, it may not be the peak, but maybe in that tapering region it will be. So that is one thing we need to understand. Another is the aerodynamic damping, as I said, whether the wind is acting as a favorable force in absorbing the energy of oscillating structure, or it is going to add more energy into structure so that it is a violent oscillation that is happening. So generally, like we use a damping value which is different from what we use for the like your seismic analysis in the case of wind. Now we have to work out what is the peak acceleration at top of the building in the along wind direction. Again, as you can see that GR that is there, that means like you are again considering if there is a resonance between the approaching wind fluctuations and the structure, then what is that you can say the acceleration that the structure is going to experience at the top level. Okay, so for the again like a reduced wind speed, a reduced like return period of 5-year return period has been suggested here, and reduced value of damping, so that like your value is on the conservative side. So that is why like they have used a lower value of damping. You can see that damping is coming in the denominator. Okay. Now again, like as I said, that a crosswind response is happening because of the your vortex excitation, and it can give to some moment, and again like what moment it is likely to have. So that can be worked out. And again, like in this case, what you require is a mode shape and the frequency which is corresponding to the across wind direction. Okay, that means you need the frequency and mode shape corresponding to the along wind oscillation, across wind oscillation. We need the frequency corresponding to the torsional vibration. These things are required with respect to the tall building. So again, one can work out the wind response and similarly the peak acceleration at the top of the structure in the across wind direction. Again, that can be worked out. And to work out the mode shape, like depending upon the type of the structure, whether it is a uniform cantilever structure or a slender frame structure, etc., or it is a building with central core and moment resisting facade, or a lattice tower, the various exponent values of K has been given so that one can do this mode shape calculation very easily without much problem. But all these things, like I'm sure that you are using some commercially available software and you can work out it without much problem. The same damping coefficient as that we discussed the along with response here also, you can use it. And how the spectral force in the across wind direction has to be used actually for square building, like for different height to breadth ratio, like these things has been given. And also like for the across rectangular building also, what is the crosswind force spectrum. These things has been worked out. In fact, these are very important parameters, the forcing function, which can be obtained by the wind tunnel testing and some subsequent analytical calculations. So there are only limited data available. So that's why, like, they have been given selectively for these, you can say, 3-4 cases, not for everything they are available. So there is definitely an issue that at present IS 875 Part 3, they have limited, you can say, details with respect to this along wind and across wind oscillation of rectangular, or in some case about the square building, not for the other shape. So the same question was there is in the morning, that only limited values are there, then what to do for the other structures. Okay. So now I am taking you to IS 16700 2023. What it says related to the wind effects. Basically, it says that for buildings with height greater than 150 meter, with complexities in plan or elevation geometry, cited in complex topography, with group effect or interference effect, and whose natural period is greater than 5 Hertz, is basically less than 1 Hertz frequency. Wind effect shall be determined, they say, site-specific wind tunnel studies. Because with respect to earthquake, we say that site-specific spectra to be obtained. So similarly, like here, they say that site-specific wind tunnel studies to be carried out. That means, like, we need to consider the terrain effect, and if some topography is to be simulated, those things are also to be considered. And also the model has to be geometrically faithful to the original structure. So when wind tunnel studies result, now the question always comes, like, when your wind tunnel studies are getting more results than IS 875 Part 3, what is to be done? They say that, like, the higher value, if you are getting from wind tunnel studies, then use them. But if you are getting very low value, for example, shear moment than calculated in IS 875 Part 3, they say that minimum design wind base shear shall be at least 70% of that derived from IS 875 Part 3. But they say that relative distribution of story shears that may be obtained from wind tunnel studies. Again, there is one important aspect, that is with respect to the torsional model motion, because the structural system that needs to be modified, that is structurally modified so as to mitigate the torsional effect, because the torsional velocity has to be brought below 0.003 radian per second for 10-year return period. Again, the damping ratio shall not be greater than 2% of critical for concrete building. I think this damping ratio we have seen, and the value for RCC structure is 2% of critical, but for the pre-stress concrete even less than that. So these are the aspects given in IS 16700, and also we calculated what is the acceleration at the tip because of a long wind and a crosswind, etc. So what is the limiting value? Like, from the acceleration, you can find out what is the drift or the deflection that is likely to happen. Again, the return period is something different, and it says that the limiting value is 1/500, and total drift at the topmost usable 4 is limited to H/500. But again, for earthquake force, it is H/250. So single story means you can go up to H/400. So these limiting values are also given. Also, IS 16700 says that if the buildings over 150 meter in height is there, then, like, the wind parameters, like they can be measured, like the wind speed, direction, etc. has to be measured, and even the acceleration at the top of the building and its direction also has to be measured. So that means apart from the wind tunnel model studies, like you need like some field instrumentation also, like if the building is over 150 meter. I'm sure that if you do a field instrumentation and if you are having data for that building over a period of time, those things will definitely help in refining the code of practices like IS 875 part 3 or even this 16700. Then another aspect I talked about is the user comfort. Actually, from serviceability consideration, basically, like what is that acceleration that is permitted? Like, again, that depends on whether it is a residential building or it is a mercantile building. So residential building, like it is the peak acceleration allowed is 0.18 meter per second square, and mercantile it is 0.25 meter per second square. So you can see that the wind load for various parameters, different return period are given. So as I discussed in the morning, like the K1 factor can be worked out for different return period, and that wind load can be taken to check these serviceability condition. Now coming to the comfort criteria, that is the human perception levels. That is, human cannot perceive motion if the acceleration is 0.05 meter per second square, but like majority of the people will perceive the motion if it is 0.1 to 0.25. Like you can just imagine, like you are traveling in an aircraft and most of the times like you don't feel that you are moving, but suddenly some turbulence is there, then you can perceive the motion. Is it so? So similarly, like if some officers or if you are working, then it becomes difficult, like if the acceleration is 0.25 to 0.4 and people may find difficult to walk or stand, etc. if it is more than 0.5 meter per second square. So they cannot tolerate motion or they are not able to walk. So these are the comfort levels one can consider, um, what will happen if the acceleration limits are exceeding, and now we have to think how we can make them within the permissible limits. So that I will discuss during the vibration control, which will be there after this aerodynamic interference. And actually, like if you see that there are two towers which are close to each other, and it is surrounded with number of tall buildings, and everywhere you will see that the buildings are not in isolation because of the land cost and other aspects, like they are always in like cluster. As you can see that almost like identical buildings, they are in cluster. So even if you say that if you decide to keep it beyond 20 times the planned dimension of the building, that may not be possible because you don't have the land available. The same problem we face like even in the power plant configuration planning. There may be a group of chimneys or cooling towers which are closely spaced because of non-availability of land, and also there are other power plant structures also there. So the presence of all these structures affect the wind forces on these structures. Now, as I said that wind may be a favorable factor or unfavorable factor. In some cases, wind interference may be a favorable effect. For example, like you have a isolated square building and you can see the pressure distribution and the vortices shed, etc. and that is giving a drag coefficient of 1.3, and you can see B is the dimension, and if it is at 4B, then what happens is that the drag coefficient becomes only 0.6. You can see this is what I said. This is the unsymmetrical pressure distribution around the body. Here also it is unsymmetrical. That is what is giving to the torsional moment, basically. The unsymmetrical pressure distribution around the body give rise to the torsional moment. But here you can see that the drag coefficient has reduced. That means this particular building, the first building, that is shielding the wind, that is shielding the second building. So that is why like the drag coefficient has reduced. But in the other case, like it is just 2B away, but it has an adverse effect. So if there is an adverse effect, that has to be taken into consideration. So how that can be taken into account for your design? So wind interference is caused by modification in the wind characteristics produced by the obstruction caused by an object or a structure in the path of wind. So like how you can, as I said, that it can have a shielding effect, okay, or like it can have an adverse effect. But this phenomena is quite complex and it can be understood only by internal studies or computational fluid dynamic studies. Okay, so in IS 875 part 3, what they have given is they have given interference factor which can be applied provided that cross-sectional shape is known to you. But if it is something unusual shape, building, etc., again for interference factor, you have to do a internal or computational fluid dynamic study. Basically, the interference factor is parameter X on a building with interfering building present to parameter X on isolated building. That parameter may be a pressure, or it may be a force like drag or lift, that is along wind or a crosswind, or it can be a moment, base moment, like bending moment or torsional moment, etc. So it can be anything. For example, if you are doing a design of a cooling tower, we are worried about the pressure distribution around that cooling tower shell. Okay, so there it is the pressure whether there is an interference factor on pressure that we try to find out. If it is a force coefficient, then we may be thinking that along wind force or a crosswind force, by which factor it has to be multiplied. For example, it has been given for both like low-rise building also. So in the case of low-rise building, like as I said, that interference effect, if they are separated, suppose the B is this long dimension, plan dimension of this building, and if they are separated by more than 20B, there is no need to consider the aerodynamic interference effect. But if we are having like closely spaced building, then the maximum increase in the wind force on the roof due to interference from similar building in case of closely spaced low-rise building with flat roof. Kindly see that this is applicable only for flat roof. That may be 25% for center to center distance between the building of 5 times the dimension. That is up to 5B, like it can be up to 1.25 times. Okay, so that is only for the flat roof of the building. Okay, so that factor is given for low-rise building, and for tall building, again they have given. Actually, if you see that they have divided the zones based on the rectangular studies, they have divided it to zone Z1, Z2, Z3, and Z4. Again, Z4, like that is something 20B distance, very low interference factor of 1.07. And zone 3, you can say that it is 1.15, and Z2 it is 1.25, and Z1 that is having the zone of maximum interference or high interference. And you can see that B is the width of the building and length of the building is 2B. So that means this is applicable only for this case, but Z1 is the maximum zone which is at, you can say 5B to 10B at that distance, and the value you can find out to be 1.345. So here basically you can see that for rectangular building with plan dimension like in the ratio of 1:2, you may be able to work out the interference factor using the data given in this particular IS 875. But again, it says that the designer may have to, can use it for some preliminary design, and also like they may carry out some specialist literature or internal study to be carried out. Now the question comes like when to do the internal testing. Actually, basically the note of the IS 875 part 3 itself says that like if you have some building or structure with unconventional shape or unusual location or abnormal environment condition, then there you cannot use it. Or if you have some structure with unsymmetric geometry where like you have to otherwise also check the torsional effects, there like you have to go for internal studies. And also they have said that like as I discussed in the morning, many of the tables given in IS 75, they are based on the data obtained on internal testing on smooth flow. So but in some cases like the values given are based on turbulent flow also. The shapes which are not given in IS 875 part 3 or some unsymmetrical geometry, etc., one has to go for internal testing. Now, when we talk about the internal studies on building, like we can do a rigid model study or pressure measurement or pressure integration study can be done. Pressure integration in the sense like you measure the pressure along the surfaces and then integrate it to get the force coefficient. Then pressure distribution over various phases of building, and by integrating the pressure, force distribution and rigid force spectra can be obtained. Peak design forces by including the resonance effect and serviceability check can also be done. Or what you can use is you can take a rigid model and then keep it on a high frequency force balance, and with which you can measure the rigid force spectra. Again, that is also another convenient method. See, what is very, very important is that the geometry has to be faithfully simulated in the internal. See, here you can see that there are some indentation along the height, or all these things are also here simulated in this model. And nearby structures, their dimensions, etc., also you should get, and everything should be, even the distance between the structure, etc., also to be properly simulated. And the third is the aeroelastic model using the strain gauge and accelerometer, etc. So actually, when you talk about the, you can say the modeling in wind tunnel, basically aeroelastic model will be the most difficult to construct, but easy interpretation of results will be possible there. But the pressure measurement studies, maybe you are easy to model it, but all those things like required the data, you can say interpretation or the computational effort required after getting the data, that will be on the higher side. Now, like IS 875 talks about this computational fluid dynamics also. Actually, when probably you can say during the last 2 decades, there is a lot of development with respect to the computational fluid dynamics and even commercial software. I think the first one was something like Fluent, and then ANSYS, etc. They have this CFD module there. And also there are basically, it is the solution of Navier-Stokes equation and direct numerical simulation with all turbulence can be, is possible, but that will be very high computational requirement, cost, etc. So that is not favorable for any industrial scale problem. And the third one, this Reynolds average Navier-Stokes, there though it is a low cost this thing, but it is not able to faithfully simulate the dynamic wind behavior. What is the most suitable is like that is the large eddy simulation, or LES, where large eddies are resolved while small eddies are modeled. Actually, we are more worried about the small eddy sizes and the fluctuations that they are causing on the structure, and high computational cost, but feasible for building application. And another important advantage with this LES method or large eddy simulation is that like it can directly simulate the dynamic wind behavior like vortex excitation and buffeting. So we were discussing about the along wind response or along wind forces, that is the buffeting, and the across wind, that is because of the vortex excitation. So both these things are possible with this large eddy simulation, and it can be resolved. So though now like the code stays only CFD, but this is the best suitable method. And again, like the ABL profile, the domain boundary has to be modeled, the structure has to be modeled, whatever inflow turbulence, and then like the building generated turbulence, etc. get. And this is the most suitable one. And you can see that this shows the eddies which are around the building, and here you can see that the building generated turbulence, that is the presence of building in the wake, how the turbulence is there, or what type of vortices are generated in the wake of the building. Those things one can obtain with this computational fluid dynamics. So the wind tunnel testing, it requires time, maybe 3-4 months time is required. Of course, there is a lot of advancement with respect to the model making, etc. Now I see that in some cases they are using even 3D printing to like design and build a, you can say a aeroelastic model. So there are a lot of improvement or advancement with respect to the wind tunnel modeling, and as well as with respect to the CFD also. Now commercial softwares are there where like you need lesser time, like to work out at least the coefficients, etc. for a closed building, that will be suitable. But if it is a open frame like structure, probably the CFD simulations will not be that accurate. Now the wind resistant design of tall buildings. As I said that the geometry is very, very important for the design of a building with respect to wind. So again, we can play with the shape of the building. So that is called the aerodynamic modification. Another possibility is the structural modification. Why? Because we say that we are concerned about the frequency which is lower than 1 Hertz. So if I try to make a tall building with frequency value more than 1, maybe that is safe with respect to like wind, but that may not be the suitable solution. That will not give you a suitable solution. The reason being that may be quite not economically viable solution. Another is the vibration control using damping devices. So we said that wind in the case of tall buildings, actually there are 2 aspects. One is with respect to the strength, serviceability and stability, and another is the user comfort. That also is quite important. So these are basically the means which are possible. That is aerodynamic design, which is a passive type of modification, that is improving the aerodynamic properties to reduce the wind force coefficient, like chamfered corners. And somebody asked me in the morning, the openings, they are basically the aerodynamic modifications. Then structural design, though like it is a passive modification, like increasing the building mass to reduce the building mass ratio, or increasing the stiffness or natural frequency, like that. But they are not that good, because the increased material cost, or it will increase bracing walls, thick members, it will result in thick members, etc. Another is addition of materials with energy dissipative properties, like that is to enhance the damping ratio of the building. And again, there are two type of um, damping devices, passive and active, like one can use. So one method is like adding auxiliary mass system to increase level of damping, like TMD, TLD. I think this particular aspect is widely used. And another is like some active control measures that are used as something like appendages, etc., added to the structure, and where the motion of that appendages can be activated so that the wind forces are controlled. That is the active control of wind-induced oscillation. So these are the overall picture, and the suitable one you can adopt. And the easiest thing I would say is that to play with the shape. So one can have, rather than, because we said that at the edge the force is, the wind is separating. So make the corners soft, okay, or tapering the structure, and provide setbacks like this. This is the Burj Khalifa where building, the tallest one with 828-meter building. So you can see the setbacks and tapering has been done. Varying cross-section shape, some spoilers can be there. Like you must have seen chimneys with some discrete strakes, etc. So that is to like minimize that vortex shedding. That is then the porosity or openings can be provided. So these are some of the shaping strategies for building, like curvilinear form or setback, tapering, adding opening, twisting, etc. You can see that these are the 2717 Burj Khalifa with that setback, some twisting, etc. Provided. Like here also you can see some geometric modification done here, like at different steps, like setbacks have been provided. So in all these structures, you can see, here you can see an opening also provided at the top of this Shanghai tower. This is 1614 feet. And I think even some building is under construction, which will be tallest, that is 1,000-meter high. So these are the Petronas tower, like Kuala Lumpur. So all these structures, like they are having some of these aerodynamic modification done. It is not that you just do something, but that has to be tested in the wind tunnel to see that that is reducing the wind force. So you can see that this is the square building in plan. You can have some fins or vented fins, or slotted corner, or chamfered corner, or you can have a corner cut provided to the square building. This is another example I just want to tell you. This is the Taipei 101 building. And what they have done to reduce the crosswind response and the drag is they have provided like corner cut, not one corner cut, but in steps, and 2 corner cuts have been provided at each corner. And you can see this is a square building, and this is the a crosswind, you can say force, RMS value of that. and this is the MC configuration. That means this geometric modification has considerably reduced the crosswind force. Similarly, the mean wind along wind force, X is in the wind direction, so this is the along wind force. Here also there is a reduction in the along wind force. That means there is 25% reduction in the base moment, and this has been done by Irwin, Professor Peter Irwin in RWDI internal, and it was reported in 2005. So you can see that by doing a proper aerodynamic modification, the along wind and across wind forces can be reduced. So that is well established. Only thing that has to be proven in the wind tunnel before you adopt it for your design. So these are the various tall buildings provided with tuned mass damper. You can see that the tuned mass damper, that is the most preferable solution, and I think because only one I can see that in 2012, they have provided a tuned liquid damper. So otherwise everywhere they are providing the tuned mass damper. Probably I read somewhere that you need some water tank at the top of the building for the fire requirement also. So that also act as a tank with some water at the top. So again, that will somewhat act like a tuned liquid damper if properly designed. So most of these buildings, so you can say that apart from aerodynamic modification, they have been provided with dampers also. That means auxiliary damping device, the passive one and aerodynamic design, they are provided to make this particular structure safe. So with this, I have come to the conclusion. So what I would like to summarize here is that basically the tall buildings, they are subjected to along wind forces, across wind forces, and torsional moment. And along wind forces, how to compute the forces for design using gust factor approach that has been given in IS 875. And then the across wind response due to vortex shedding for a particular shape building, square and rectangular, that has been given. For other buildings, you need to go for wind tunnel testing. But another new initiative that is being undertaken is that people prepare a database, because wind tunnel testing is a time consuming and it requires some financial requirement also. So what people are trying to do is they are trying to create a database of the building shape along with the properties, etc. So if such, that is why people say you refer to specialist literature. But if you are searching for a literature, you may not get it on that particular day. So it is better that people are designing, and some of you must have done some internal testing, but that may not be available to other users or other designers. But if we are trying to prepare a database that with the shape of the building, size of the building, the dynamic properties, etc., that will definitely help us not only to use that for the design, but also that will help us in improving the IS 875 Part 3 or IS 16700, etc. And also if you have the field instrumentation done for any of your building which is more than 150 meter high, if you can share those things with probably the committee which is dealing with the modification of IS 875 or CED 37, in BIS, probably those things will add value in improving the codal practices, because what we require is the actual data actual results of the pressure distribution or force coefficients, or even the field monitoring results, or the spectral energy content in along wind direction, across wind direction, etc., to be included in the codal practices. So that will definitely help you to do a better design of these structures. So thank you, and I'm open for questions. I'm sure that there will be a lot of questions in this session.
Okay, thank you, madam, for a wonderful presentation, and it was absolutely spot on. We have few questions to start with. Actually, few participants have asked whether this recording will be available. Yes, it will be available on YouTube channel of EFC. You can visit that YouTube channel after a week, and it will be available. Uh, okay. I don't know about this question, but madam, how is this applied in analysis of long steel footbridge at say 10-meter height? Is the question.
Long 10 meter, what is that?
Long footbridge at a height of 10-meter. How this is applied means probably he's asking for all the principles of design.
Actually, that is a footbridge is a different category. In fact, again, it depends on what type of footbridge it is. And also there, the human induced vibration, that is also important. So without knowing which type of bridge, it is very difficult to
Right.
comment on. But IRC 6 has improved, now recently revised, and that gives the latest wind forces which are to be considered for the bridges of up to, you can say, 200 meter. But we have also brought out one guideline for cable stayed bridge and extradose bridge also. So that has dedicated chapters on wind for both these bridges. And another improvement which has been done by the Steel Bridge Committee is to how to account for the human-induced vibration effect for footbridge design. So some of these documents are under print, so may be available by later 2025.
Okay. So next question is that is damping of structure definition same for both wind load and earthquake load?
No, the one which are to be used, they are different. As I explained, I think Professor Yogendra Singh has explained what damping to be considered for the seismic design. They are different actually.
Do we need to consider the gust factor if and only if both the conditions are satisfied, that is frequency less than 1 and H by B ratio greater than 5?
See, the question is that gust factor has two components. One is the resonant component and the background component. So the resonant component will give be prominent if the frequency value is lower than 1 hertz only. Okay, so otherwise the background factor is sufficient. That is like if one condition is satisfying but frequency is not is more than 1, probably only the background factor will be sufficient, because the other one will be quite small compared to the background component.
Right. Okay, the next question is, do we need to apply 100% along wind and 100% across wind loads worked out as per IS 875 part 3?
875 now gives that you have to apply both 100% along wind and across wind. That is what is stated there. But actually, if you really look into it, like across wind will be happening at a wind speed which is lower than the design wind speed, and the along wind is basically the buffeting. So it may be there at the, you can say at the peak, but now it says that both has to be considered together. Yes.
Right. Okay, the next question is, how can we take care of wind load consideration for considering the future development, since the future expansion will not be known during design? That's a bit tricky situation.
Yeah, future expansion. Actually, like if you, what I have seen is that because I have done number of power plant structure internal study. So though there like the chimney has not been built or they are not going to build, but they say that this particular location, there will be a chimney of this height. Okay. So it is better that the future plan should be given, a complete future plan to be given for the internal testing, then only the result will be correct. Otherwise, whatever you are getting will not be of much use.
Right. So the next question is that when we are doing wind design using ETABS model for the static wind, shall we consider the coefficients from table 5, that is pressure coefficient, or from figure 4, that is force coefficient? So I think that again depends on the height of the building. If your building is low rise, you should consider
Yes.
pressure coefficients, and if
Yes,
your
yes.
building is high rise, you should go with force coefficients. The- How do we apply the effect of tune dampers in analysis model like in ETABS?
I think first thing is one has to decide how much damping to be enhanced, then how the mode shapes are affected with the placement of the dampers. Those things can be studied, and that will help in finding out how much reduction in the amplitude of the motion.
There's a question that can we determine the interference factor without knowing the exact height and position of the peripheral structures?
No, it is not possible. That's why I said that if you are planning, then that at least like you may be building a tower later, but still the position and height has to be there. Otherwise, it is not possible.
Right. Because the word interference itself make it very clear.
Yes, yes, yes.
So during gust wind calculation, which time period shall we consider? It is the
It is
calculated
an
from ETAB
hourly.
model or from natural time period formula by IS code, whether it is program calculated or whether
If
it
you
is.
are you are doing a program calculation, that can be used. This is only for like easy judgment, etc. That thing is given. Otherwise, like if you are using a computer program, you can use. Only thing like you have to remember that you have to consider the frequency and not the time period for wind calculation. That's all. And the frequencies which are lower than 1 hertz, and in the long wind direction, what is the uh, frequency and mode shape across wind and the torsional direction. These three becomes important with respect to wind of building.
Yeah.
I'm on this subject only, but while doing program, basically people are not modeling the infills wherever they are. So that program wind may give the more flexible
No,
structure.
the modeling has to be correct.
Correct. So that is the major
That
issue.
part
The
I don't know about it. That's why I said.
the program
But if you are
calculated,
no,
yeah.
no, but
Correct.
yeah,
So
one should
people,
not manipulate the mode shapes and
no, it's not
frequency. Then
manipulation as such,
not
but
be no, we will not be getting the clear picture of
correct,
wind.
correct.
Yeah,
That's
yeah.
why.
To use the correct word as per the this thing, it has to be a faithful modeling.
Yes,
Yeah.
faithful modeling has to be not only geometrically, but structurally also faithful mathematical modeling to be done. That will be the
Right.
correct thing. Yes.
Okay, there's one question that, ma'am, while design of tall structures, from where we should consider the height if there are two basements and one podium? This height you mean for the time period calculation? I don't know whether if it is for time period calculation, it should be from the base. Okay, then we go to the next question. Mm, Okay, man, to conduct research on various aerodynamic modifications, where can we conduct wind tunnel tests?
Wind tunnels are available in India, uh, like in research purpose, it is there in SCRC Madras or Chennai. There is one wind tunnel there. Then there is one wind tunnel in the uh, JP University in uh, Pune. There is a wind tunnel there. Then there is one wind tunnel in IIT Roorkee, and one wind tunnel is there in IIT Kanpur, but that is an aero space department, so it is mainly used for, you can say, aeronautical studies. So I'm not sure about the time availability. Then there is maybe some small wind tunnels are there in some of the universities, etc. They are also available for research. But commercial wind tunnel, I think there is one in um, Trivandrum with RWDI.
Right.
And IAC Bangalore, they have a wind tunnel, again an aeronautical wind tunnel. But earlier, the wind tunnel studies were done for even buildings and structures in that wind tunnel.
Oh, so we come to the last question. In AC, wind is considered for different angles. Why in IS code it is only orthogonal directions? Both these codes have directional coefficients, that is KD. The American code uses different angles for wind load calculations, whereas IS code uses only orthogonal directions. That's the question.
Wind directionality, it can come from any direction. And if you see the pressure coefficients, etc., see basically how you study the wind directionality effect is you place the model on a turntable and then rotate the turntable at say 15 degree, etc. So you do it at 360 degree and then find out what is the maximum forces like force coefficient or maximum pressure happening. You find out what is the you can say most probable direction which you have to consider for your design. So that value you have to take. Okay, so if you see the ES 875 pressure charts, etc., they are also giving for various direction. So one can judiciously select which one for your design after looking into that tables.
Right. Thank you, madam.
Madam, I have one question. Actually, it is for to our morning session. This is related to wind on crane structures during erection. So crane or like thing. So during erection, obviously, it is not expected that it is operated in say very windy conditions or something. But still, we have to apply some wind. So are there any guidelines for that?
You are talking about the lattice structure.
Lattice structures or any
Lattice structure.
even plate girders hanged on the crane, which
Yes,
are
yes,
to,
yes.
which
I
are to
understand.
be.
In fact, we designed a mobile bridge inspection unit for the usage. But there again, we considered the wind because that again will be there. But only thing is that these things during high wind, it is not advisable.
Yeah, that's true. But some wind we have to take.
Yeah, but I think we
Yeah,
can
but
treat
the other
it.
one is like your crane, etc., like the lattice frames which are there in IS 875. Based on the solidity ratio, the force coefficient can be taken, and then you can do the uh, design for that. And another aspect is that, like if you are talking about the plate girder, etc., connected to it, so the forces on that also, wind force acting on that girder also to be considered in the lifted position.
But those are for either permanent structures or
Yeah, it has to
temporary
be
structures.
Temporary structure.
You
There
have
is
to treat
a
as a temporary
temporary
structure.
structure
But even
code for
temporary structure is also 0.7 times the maximum
yes,
wind
yes, yes.
speed. But that also is not expected during erection because nobody does the erection in such stormy winds. Is there any value for normal winds? Yeah.
Actually, like the return period, what you
Return period
consider
is
is on the lower side.
lower
Lower
side.
side, yeah.
And but there is a temporary structure code for in the case of bridges that is there.
Mhm.
So that probably gives some values for this
Okay.
also.
Okay, we check. Yeah.
So your low return period will reduce the wind load drastically. Actually, even though
Correct.
it is 70%, but
Five,
still the
five, 5 years.
5
Actually,
years.
only
Yeah,
problem with
5 years
the
is 70%, but 70% is also too high for say erection crane. Yeah, or something like that. Fine. Okay, we go ahead.
I think, yeah, we are finished with the
Yeah.
questions, and over to you, Rashmi.
Thank you, sir. Thank you, Lakshmi ma'am, for your wonderful presentation.
thank you.
And thank you, Anand sir, for moderating the questions and
Thank you.
uh, I mean, taking words of participants and asking the queries, each and every query to the ma'am. And thank you, ma'am, for the explanation of all the questions of participants. And I would like to invite Dr. Yogendra Singh for his next presentation. And the topic will be analysis of buildings for earthquake forces and changes in the revised code on capacity design and concept of overstrength design. Hand over to you, Yogendra sir.
Thank you. Thank you very much, and good afternoon. I will just share my screen. And I guess my screen is visible. I will make it full screen. Okay, so we are into our second talk now, and I have slightly focused this more on capacity design of tall buildings, because analysis and design of tall buildings is a much wide topic to cover in 1.5 hours. So I thought I will focus on this new concept which is coming in our revised code, that is overstrength factors. So we have to design with overstrength load combinations, and the basis for that is in capacity design. So why we need capacity design? Why not to design directly for the forces which we are getting? So the reason for that is that in case of RCC members, not all the modes of failures are ductile. For example, any RCC member can fail either in flexure or in shear or in a combination of axial force and flexure. So bending or flexure is a ductile mode, but shear is a very brittle mode. And it is quite contrary to steel. In case of steel, shear mode is very ductile. In fact, more ductile than flexure. But in RCC, the shear mode of failure is very brittle mode. So that is to be avoided. Then PM interaction, if there is axial force also acting on a member, RCC member, that means in place of beam, if we are having a column, then also the ductility is reduced. And presence of shear force also reduces the ductility, particularly when the shear force is close to the shear capacity. So a small shear force is not that much a problem, but if we are having large shear force just closer to the shear capacity, when the failure may start in fracture, but later on it may be when the concrete cracks, it may be taken over by the shear failure. So there also the ductility is reduced significantly. And then beam column joints and beam wall joints, those are prone to brittle shear failure. In the joint region, very high shear force develop, and the joints are susceptible to failure in shear. Then slab column joints or the flat slab construction. So there the joints are susceptible to brittle punching shear failure. So all these brittle modes are to be avoided, and the desirable mode, that is only the flexural mode in this case. So that is to be promoted. That we have to ensure that failure takes place in ductile mode, in flexural mode, and all other modes, brittle modes, are to be avoided. Now, how we can ensure that? So this is an analogy with a chain in which there are several links and only one link, this darker link here, this is ductile, all other links are brittle, and it is subjected to a large force which is more than the capacity of this chain. So this large force, you can think like an earthquake. I told that earthquake is a large force, and generally more than the capacity of the structure. So in that case, if it is more than the capacity of the link or capacity of the chain, then the chain is going to fail. Now, only one link is ductile, that is our bending mode of failure. All other failure modes, which are represented by different links, those are brittle. So how the failure of this chain will occur, whether it will be brittle or ductile. So answer to that question will depend upon which link is going to fail. If the link, the brittle link is going to fail, the failure will be brittle. If the ductile link is going to fail, then the failure will be ductile. And how we can ensure that only the ductile link is failing? For that, we have to make brittle links stronger than the ductile link. This is the concept of capacity design, where these brittle links we are not making stronger than the earthquake force. Earthquake force can still be much larger, but we are making these brittle links stronger than the ductile link. And then the failure is located in this ductile link. In case of a structure, in the flexural failure of beams. So that is our desirable failure modes, and all other modes should be stronger than that mode, so that proper we can get ductility and energy dissipation. So how this is achieved, it is there in the current code also. We ensure that the beams fail in flexion, beams do not fail in shear, because shear is a brittle link, and for that we calculate the capacity shear. It is implemented in software also, and all of us have been doing this. The other criteria is that columns are having smaller ductility, lower ductility than the beams, because as I said, in presence of axial force, the ductility reduces. So columns are less ductile as compared to beams, and that ductility in the columns depends upon the axial force. So if axial force is very large in the compression control range, then the ductility is further less, because the failure is due to crushing of concrete. So that's why the code limits the axial force in the columns up to 0.4 VDFCK, so that it is in the tension control range in the PM interaction curve, and some ductility is available. But even then, the ductility available in the columns is less than what we are having in case of beams. And another issue with column failure is that columns can fail in story sway mechanism, where the columns of, as soon as the columns of a single story fail, the building will collapse. Whereas in case of beams, the mechanism will form when all the beams are yielded, and then the hinges form at the base in the columns. Then the mechanism occurs, and the structure fails. So much larger number of hinges are forming in the second mechanism, and the structure will be able to dissipate much more energy before collapse, and it will be able to withstand larger forces. So this is our desirable mechanism, and this we achieve by making the columns stronger than the beams. Again, columns we are not making stronger than the earthquake. We are making these stronger than the beams, so that the columns fail, beams yield much before the failure of the columns. And here we have to understand that the actual capacity of the beams is going to be larger than what we are designing for. And that's because there is a strain hardening in the steel, and there is a variability in the strength. So that over strength needs to be considered when we are comparing the strength of beam and column. So whatever is the plastic capacity of the beam, that needs to be multiplied by a factor. And in our code, that factor is 1.4. So we consider the total moment capacity of the beams which are connecting into a joint, and then we calculate the moment capacity of the columns, and the capacity of the columns should be more than 1.4 times the capacity of the beams. And in some joints, interior joints, there are two columns and two beams meeting, whereas in some cases there may be one beam or one column. And in case of a single story building or at the roof, there may be single column and single beam. So all the beams and columns which are joining into the member, all those are or their capacities are summed up. Now, another common issue related to detailing is that when we are detailing our vertical members, then whether that member is to be considered as beam or column. So, sorry, it is to be considered as column or shear wall. So that can be identified by looking at the bending moment diagram. So in case of a column, we see that there is a point of contraflexion near the mid-height or mid-story level, and the moment is changing the direction there. So if it is tension is on one side, let us say right side at the top, in the bottom portion it will be left side. Similarly, in beams also, there is point of contraflexion along the near the midspan, and the bending moment is changing the shape. On the other hand, in case of a shear wall, if shear wall is connected to the beams, like this is the variation of the bending moment in case of a coupled shear wall. So coupling beams are quite rigid beams. So those can cause a jump or a variation, sudden change in the variation of the bending moment diagram. But we do not get point of contraflexion. So the moment may change direction at one or two locations along the height, but for most of the height of the building or the shear wall, the it is bending in single curvature. The bending moment is on one side only, or it is causing tension on one face, not on the other face. So this is the basic difference. Shear walls are bending in single curvature, whereas columns are bending in double curvature, and those are having point of contraflexion in each story. Shear walls, on the other hand, may not have any point of contraflexion, or at least in the lower two-third height, there is no point of contraflexion. So this definition has been included now in the revised code, IS 13920, part 5, that is for buildings, and 2025 we may say, which is going to come. So there this definition is included, although there appears to be some typing issues still, that will be perhaps taken care of. So what it says that if a vertical member is in single curvature along the full height, and the single curvature may be about any of the major or minor axis. So that means that if it is having single curvature along major axis and double curvature along the minor axis, still it will be considered shear wall. So in case of shear wall, it is possible that in out of plane bending it may undergo double curvature, whereas in plane bending it may be in single curvature. Similarly, if it is in double curvature about any of the major axes, so here in case of columns, actually it should be about both the major and minor axes. So if it is in double curvature about in both the directions, about both the axes, then it will qualify as column. If it is having single curvature about any axis, like a shear wall in outer plane can be double curvature, in plane it can be in single curvature. So that will be shear wall. So it is the variation of the curvature, and single curvature should be at least in two-thirds of the bottom story. Then it will be considered as shear wall, and we can apply the shear wall detailing to those members. Now, shear wall can also come with openings, and then it becomes a little complex because the portions of the shear walls behave as spandrels and piers. So in the left figure, the shaded portion is showing the spandrels. Spandrels are basically behaving like beams or coupling beams, to be more accurate, whereas the vertical elements which are shown in this right figure by the shaded area, these are acting like columns, and their detailing is also, and these will bend in double curvature. So when this type of shear wall will be subjected to lateral load, actually this shaded portion, the piers, these will bend in double curvature, and accordingly these need to be detailed. Now, if we look at the failure modes of shear walls, one of the failure mode is crushing of concrete. So crushing of concrete mostly occurs because of the loss of the confinement. So when the confinement is lost, the concrete becomes unconfined, its crushing strength reduces, and then it is subjected to crushing. So proper confining in the, especially near the boundaries where extreme stresses are going to develop, is necessary. And all the codes, including our revised code, takes care of that. And here, this is taken from ACI 318. So this confining is shown in the boundary element, and this boundary element has to be minimum 2 times the width, and confining reinforcement similar to what we provide in column has to be provided here. So this is a special confining reinforcement, but the remaining portion of the shear wall, that should also be provided with ties. So this may not be calculated according to special confining reinforcement, but constrained to the longitudinal vertical bars against lateral buckling, that needs to be provided. So if there is a long boundary zone, then we can, I will come to the length of calculation of length of the boundary zones slightly later. But if it is a long boundary zone, then we may provide 2 hoops here and some ties. And one question which people have been asking regarding detailing, that whether the size of the bar which is making these hoops and ties has to be same or not. So please note that actually the purpose of these stirrups and ties is to provide the confining pressure on the concrete. And confining pressure on the concrete depends upon the total amount of the confinement, which comes from the stirrups as well as ties. So some of the codes, they talk about the transverse reinforcement ratio. That means the total reinforcement which is provided in the transverse direction. So that takes into account the area of all the ties and stirrups, whether those are of equal size or unequal size, total force, we can calculate the confining pressure which it is applying, we can calculate. But our code calculates the size of the bar which is used to provide stirrups and ties. So that calculation is based on assuming equal diameter of the ties and bars. So theoretically, there is no problem. We can provide unequal size of ties and stirrups, but the formula which we are using in our code to calculate the diameter of the bar or the area of the bar which we are using to form these stirrups and ties, that is based on the assumption that these are of equal size. So same size bar is to be used in tie and stirrups. In fact, the revised code, revised 13920 is making that clear.
Sir, one more
Yeah.
question. Sorry to interrupt you.
Please.
There's also this transfer reinforcement needs to be completely anchored inside the boundary element, because there is a lot of confusion about this. People.
I am coming. You mean the horizontal reinforcement?
Yeah. Right.
Yeah, that is also a failure mode. I will come to that in next slide. One of the next slides. Then another failure which has been observed is buckling, out of plane buckling of the shear walls. This is particularly true for thin shear walls, like the My1 construction we are having. So if the shear wall is thin, then under compression it is prone to buckle in the out of plane direction. So here you can see that all the reinforcement, including the confining reinforcement, is intact. Still, it has got crushed because of the buckling. So minimum thickness is to be controlled. To avoid this thickness, which is shown here as B in this diagram, and the story height HU. So this B ratio of HU to B, that needs to be controlled, because what will happen, it will be subjected to cracking when it is in tension, and then when the earthquake will reverse its direction, it will undergo compression, and this tension and compression is interchangeable. As a result, it will crack, especially the bottom story, and after cracking, it is going to buckle. So to avoid that, there should be sufficient thickness of the shear wall, and this is the diagram which is governing the buckling. So this diagram shows on x-axis we have maximum tensile strain which is developing when earthquake is acting in one direction, and then the aspect ratio. So depending on what maximum strain we are permitting, and the practical range is shown here. So in this range, we can see that if the slenderness is in this range from here to here, this is the practical range. And ACI 318 provides a ratio of HU by 16. So B is HU by 16. So this is the line which is showing the ACI 318 limit. And Moyle has suggested in his book and some research papers that it is recommended that HU by B should be less than 10. What does that mean? That if we are having a, let us say, a 3-meter story height, then the shear wall thickness cannot be less than 300 millimeter in the bottom story where the hinge formation will take place. And those areas where the hinge formation is not taking place, it can be 1 by 16. That means up to 200 we can allow. That's the recommendation of Moyle. Eurocode 8 says that the minimum thickness has to be 8 inches, 200 millimeter. And it is also checked that it should not exceed, if the length of confined portion does not exceed 2B, then this is to be B should be HU by 15, and if it is 0.2 LW, then it should be HU by 10. Our code, the code under revision, that is also coming up with these requirements, and it gives the minimum thickness of spatial shear wall. So those shear walls which are used to resist lateral load, the thickness will be minimum 150 mm. So when we are talking about design of my one structures with the formulae or the methodology used for shear walls, we have to keep this in mind, that the minimum thickness is 150 millimeter and 300 millimeter for coupled shear walls. So if these are planar shear walls without opening, it is 150 millimeter, and if it is to be used as coupled shear wall, then 300 millimeter. And this is to be also checked for the fire resistance requirements of IS 456. And the minimum ratio of length of wall to its thickness will be 4. So length is along the or in plane dimension of the cross section. So that ratio should be minimum 4. Then if the thickness is, in the revised code 13920/2000, okay, this I have printed wrong here. It is 2025, the one which is under revision. So that is giving that minimum 200 millimeter. Earlier existing code, it is 150 millimeter. In the revised code, it is 200 millimeter. So minimum 200 millimeter thickness is required if there is no beam connected perpendicular to the wall. So if there is a beam connected perpendicular to the wall, then these requirements of the beam column joint, those will be applicable to shear walls also. So in that case, thickness cannot be less than 20 times dV, 23 times dV, 26 times dV, depending upon which grade of steel we are using. So if we are using Fe 500 grade, then 23 times dV. dV is the diameter of the longitudinal reinforcement in the beam. So 23 times dV will be the thickness if we are connecting a perpendicular beam to the shear wall, and 300 millimeter in case of coupled shear wall, and 1 by 16th of HU. That means HU by B ratio 1 by 16, where HU is the unsupported height of each story. And then fire resistance coming from requirement coming from IS 456. So we can see these clauses are much more stringent. 200 millimeter will be the minimum thickness as per new code. And then the point which Mr. Kulkarni was talking about regarding the anchorage. So this anchorage of the horizontal reinforcement into the boundary element is very important. It is to be fully developed. So in case of ACI, there is a standard 90-degree band where this length is LDH. So this is to be provided LDH. If we are banding it like this, if we are not banding it at 90 degree, then it should be equal to the full development length. So the horizontal reinforcement, this will be resisting shear, and it should be fully developed into this confined boundary element so that it is not slipped. Otherwise, it will slip and it will fail in shear. The shear wall will fail in shear. Then there is a need to have higher reinforcement near the boundaries, because if we are having lightly reinforced walls, so if the reinforcement is same here and it is light, so in case of lightly reinforced wall, we have this concentration of strain. So the crack width is much larger. Are fewer cracks, and the crack width is much larger. And as a result, we are not able to get good ductility. So the cracks should be. It is desirable that the cracks should be distributed. And for these cracks to be distributed, there has to be a minimum longitudinal reinforcement provided here. So in the boundary element, the minimum reinforcement, similar to what we expect in case of columns, 0.8%. So that much reinforcement is to be provided in the boundary element. So near the boundaries, a concentrated a concentration of the reinforcement up to 0.8%, minimum 0.8% is required from the ductility point of view. Otherwise, this curvature which we are getting, ultimate curvature which we are getting, will be much less. Now, if in case of a shear wall where there is no need of this confining reinforcement from the stress point of view, even then the code is suggesting that there should be minimum 4 bars here, and those 4 bars should be confined together. So earlier the code was talking about 2 bars. Now the code is talking about 4 bars to be provided, even if we don't need boundary element confinement. Now in ACI 318, the length of this boundary element is given as 15% of the length, where concentration of concentrated reinforcement is needed in different plan shapes of the shear wall. So the width or thickness of this boundary zone may be same as of the shear wall. It may be larger than that of the shear wall, but the length has to be 15% of the total length. And in the bottom portion here, there will be special confining reinforcement similar to what we are using, a special confining reinforcement in the columns. And as the stress is reduced along the height, the confining reinforcement may go on reducing. And if the stress is below the limit specified in the code, then nominal confining reinforcement may be provided. When we are having openings, then the sides of this opening, those are also acting as boundary elements. So there also confining reinforcement is needed. So for the overall bending of the wall, these are the boundary elements where confining reinforcement will be required, and smaller elements of the height of this boundary element, of this opening, those needs to be provided here also. Now, as per IS 13920 revised, this is 2025 part 5. The width of the boundary element, that means thickness of the boundary element, should be, if it is of the same thickness as that of the wall, then the boundary wall is concealed. And in that case, no beam can frame into boundary element in the perpendicular direction. If the frames are there, or the beams are framing in the perpendicular direction into the boundary elements, then these requirements of the thickness are applicable. That means if you do not want to provide the full thickness of the shear wall equal to this, which is required from the diameter of the beams framing into the shear wall in perpendicular direction, you can provide boundary elements at those locations. So thicker elements you can provide along the alignment of the beam, and rest of the thickness can be the minimum thickness required from the code. And if the diameter of the longitudinal bar or 300 millimeters. So in this case, in no case it will be less than 300 millimeter if the beams in the perpendicular direction are joining the shear wall. And when the geometry of the wall and its end project in the perpendicular direction, so sometimes there may be larger elements, larger depth element, and then up to 3 times the thickness of the web can be considered as part of the web. Or if it is larger, then it is to be treated as L or T wall. So if it is L shape or T shape wall with smaller dimension of the flanges, then up to 3 times of the web thickness we can consider in the boundary element. Then regarding the length of the boundary element, the code has the revised code has 3 clauses. It has to be equal to twice the thickness of the web and 500 millimeter, and equal to the length with in which the nominal stress is more than 0.2 FCK. So this clause is already existing in our code, the current code also. So that clause will be there. And along the height, if it is reduced below 0.15 FCK, at that location we can perhaps terminate. Then another type of failure which has been seen in past earthquakes is along the construction joints. So any RCC element, vertical element, is to be constructed in lifts, and at the junction of these lifts there is a cold joint, and there is a tendency at this cold joint to slide. So there has to be a minimum reinforcement at this joint, across this joint, which will act as dowel and which can prevent the sliding failure. So it will be subjected to shear failure here, and these vertical reinforcement will act as dowel. And minimum reinforcement, which is this clause is already there in our IS 13920/2016 also, that the reinforcement which is to be calculated AST by AG. So this becomes the percentage or fraction of the area given by this formula. So this minimum reinforcement is to be provided at the construction point. Now, there are a few issues which are still missing in our code, and unfortunately those issues are missing in the code which is under revision also. And one such issue is that the mode shape of the shear wall changes once the hinge forms at the base. So shear wall we are designing and detailing in such a way that the hinges are forming at the base. Even when we are designing coupled shear walls, so in coupled shear walls, first the coupling beams are supposed to yield, and then the hinge will form at the base of the shear wall. So once the base of the shear wall develops hinge, its mode shape changes, and the resultant of the horizontal force reduces in height. So here you can see that the mode shape will be like this when it is pinned at the base. So due to that, the shape of the bending moment changes, and bending moment at near the mid height, that goes on increasing. Initially, the shear wall is acting like a cantilever, and the bending moment diagram is more or less triangular, like that in case of a cantilever. But as the yielding occurs and more plastic deformation occurs, the shape of the bending moment goes on changing like this. And in the bottom portion, it becomes more or less constant, and then it is reduces triangle. If we look at the shear force, then the shear force variation is also changing, and the shear force in the bottom, because the resultant force has shifted to a lower height. So for the same bending moment, now larger shear force will develop, and this developed shear force increases tremendously. So we have to ensure that even after yielding of the shear wall at the base, the shear failure should not occur. We should have adequate shear capacity in the shear wall. Now, ACI 318 suggests these envelopes for bending moment and shear force, and the bending moment is calculated from the provided moment capacity, and then the shear wall is shear force or shear force diagram is amplified, and this amplification factor or the amplified shear force is given as dE, and this is capital omega V and small omega v times Vu, where Vu is the ultimate capacity, provided capacity. So whatever capacity, this is the design capacity, and this is the provided shear strength. I will explain. And this is the dynamic amplification factor. And the upper limit on the amplified shear force is 3 times the design shear strength, design shear demand, which we are obtaining from the analysis. And this capital omega, this is provided over strength. So this provided over strength, if the shear wall is slender, height of the shear wall to the length of the shear wall is more than 1.5, then it will be minimum 1.5, or the ratio of the actual provided moment capacity to the design demand. So design demand MU, which is coming from the analysis, and MPR, the provided moment, which we will calculate from the actually provided reinforcement. And generally we end up providing more reinforcement, more vertical reinforcement in the shear wall, and this factor is anywhere between 1.5 to 2, or maybe even more than 2. So this factor is to be considered. So capital omega is taking the actual ratio over strength which we have provided, and this omega v, small omega v, this is considering the dynamic amplification factor. What is the dynamic amplification factor? Because of the change of the mode shape and the bending moment diagram. So due to the change in the bending moment diagram, the shear force in the bottom portion increases. So that increase is taken into account by this small omega v, and expression for this small omega v depending upon the number of stories. If number of stories is less than 6, then this formula, usually we will be having number of stories greater than 6. So actually this formula will be there, and maximum value suggested is 1.8 and minimum value will be 1.3. So between 1.3 and 1.8, this is the dynamic amplification factor. So actual over strength factor multiplied by dynamic amplification factor, that much amplification in shear force is to be done. Now, Moyle has suggested a change in the bending moment diagram also, an amplification in the bending moment diagram also, because it is possible that the first hinge forms at the base, and then later on the bending moment as it is changing, I have shown as the ductility demand increases on the bottom hinge, the bending moment along the height of the shear wall is changing, and it is possible that another hinge, flexural hinge, may form somewhere along the height of the shear wall. So to avoid that, the bending moment diagram also needs to be modified, and this modification is suggested that in the bottom portion up to a critical height, which is roughly equal to height of a single story, the bending moment will be constant. That means constant reinforcement will be there. And this is the actual provided MNS, this is the actual provided moment capacity at the base. Then if we have provided a higher capacity at the base, the capacity in the upper portion should be increased not only by the same proportion, but by this bending moment diagram. So this bending moment diagram is obtained by continuing the same reinforcement up to a critical height, and then drawing a line which is proportional to this provided bending moment diagram. So there is an amplification of demand in the upper portion based on how much increment we are providing here. Suppose there was no increment here, we were providing exactly the same moment capacity as required by the design, then the design bending moment shape would have been same. But because we have provided a overcapacity here, so due to this overcapacity, the demand in the upper portion of the shear wall will also increase. So this amplification is to be considered not only in shear force, but also in bending moment. That is suggestion by Moyle. It is still not included even in ACI 318, because in ACI 318 also, if you see the shape of the bending moment diagram, if you see here, this is same as the original multiplied by only the overstrength, provided overstrength. So this much is the provided overstrength. Priestley has done a lot of work on that, and different intensity levels of earthquake, the shear wall bending moment diagrams are plotted. So you can see that the shape of the bending moment, which is initially triangular, goes on changing, and at a ductility demand of 2, the ratio of 2, you can see that it is almost vertical right up to the mid height of the shear wall. So the demand becomes constant. So if we have provided reinforcement detailing corresponding to a triangular bending moment diagram, another hinge will form here. And to avoid that, and accordingly the shear force is also increasing. So in Eurocode, those recommendations are included, and Eurocode provides a bending moment envelope, something like this, where the bending moment, what is provided at the base, that is continued up to this height A1, which is called tension shift. It is roughly equal to the length of the shear wall, the larger horizontal dimension of the shear wall. So up to that length, it is continued to be constant, and then it is parallel to straight line design moment. So procedure to develop this moment envelope is described in Eurocode, and similar procedure is there for shear wall, for shear force also. And here the shear force is not taken similar to what is there in ACI as triangular. So it is continued with the triangular shape up to only 1/3 of the height of the shear wall. And in the top 1/3, the design shear is taken to be constant, same as the value which is there at 1/3 of the height. So these requirements, these guidelines regarding design of shear walls are still lacking in even in ACI 318, and our code, although it has come out with some guidelines, the revised code, but still these guidelines will not be there. So we have to be careful in designing shear wall, and we have to follow ACI 318 or Eurocode for improved design. So our code, in place of calculating the bending moment diagram, it has come out with an overstrength factor. So this overstrength factor will be taken care of through these overstrength load combinations. So what the code says that in zone 3, 4, 5, and 6, the structures are to be designed with this overstrength factor. And this overstrength factor will be applied on the earthquake force. The total earthquake force, 130-30 rule, 100% in one direction and 30% in the other two directions, and that will be multiplied by omega. And this value of omega is given in the code. So in case of columns in the building having a special moment adjusting frame, the overstrength factor will be 2. And beam to column and beam to wall joints, which are part of SMR of SSW, those will also be designed for this factor 2. So this factor 2 will be used for shear design of the columns, and it will be also be used for design of the beam column joint. And the foundation of the column will also be designed for this overstrength factor of 2. So if we have to follow the guidelines of ACI or Eurocode, we have to calculate the actual provided overstrength factor. Whereas the maximum value there is 3 in case of shear wall. So our code, the revised code, is now suggesting that we have to do strong column weak beam design ratio 1.4. In addition to that, we have to also design the columns for 2 times the design force which we will get from the analysis. So column has to be stronger than the beam, and there is a reason why this additional factor is there, because when we are using a strong column weak beam design, we are considering the rectangular beam, and actually the beam is having slab acting as flange, and due to that the strength of the beam is underestimated. So that was missing when we were doing 1.4 times the beam strength in the column. Still, our beams were not weaker than the columns, and it was not possible to achieve strong beam weak beam column. So this factor of 2 will take into account all those hidden strengths which are there. So with this factor, hopefully we will be able to achieve a strong column weak beam. The main issue is in the shear wall. So in case of shear wall, also an overstrength factor of 3 is provided if it is slender wall. So when the height of the wall to length of the wall is greater than 2, if it is slender, then it will be the ratio, this overstrength factor is 3. So you can compare it with the ACI 318, where the upper limit on the overstrength, shear overstrength factor was 3. So this factor 3 will be used for designing of shear wall in shear. So whatever flexure design we have done, when we will be checking for shear, we have to check with this overstrength factor. And in case of short shear wall, squat shear wall, the design of which is governed by shear, there this factor is 2. So even the squat shear wall, we have to design with this factor of 2. Although their design is governed by shear only, and response reduction factor there will not be used because the failure will occur in shear. Still, we have to use this overstrength factor of 2. Then there is issue regarding out-of-plane bandings. There is a lot of confusion in the design fraternity whether we should consider out-of-plane banding in the shear walls or not. So shear walls will also be subjected to out-of-plane banding, especially when these are connecting the out-of-plane beams. Beams are connecting at top and bottom. So due to that, out-of-plane, significant out-of-plane moments can develop. So ACI 318 makes clear that, and our code also now makes it clear, that the shear wall will be designed similar to column, considering PM1, M2 interaction. So axial force and bending moment in the 2 directions we will consider, and the shear wall will be designed accordingly. Now, if we are having a beam connected to the shear wall in perpendicular direction like this, then the code, revised code says that the thickness has to be 23 times dV. So that 23 times dV may not be the thickness of the shear wall available. In that case, we have to run a vertical element like this, and this vertical element will take care of the 23 times dV. Now, another complex detailing issue is coupled shear wall. So coupled shear walls are having the advantage of combining the stiffness of 2 shear walls. So if I have 2 independent shear walls, their moment of inertia will be sum of the 2 shear walls. But if I join these shear walls together, then the effective length will become 2 times, and the moment of inertia will increase 4 times, or sorry, 8 times, because it is 2BQ. So, and oh, sorry, here it was 2, so it will increase 4 times finally. And if I'm having a shear wall coupled by beams like this, then it will be somewhere in between. So the moment of inertia and strength is going to increase tremendously if I can connect these shear walls by short beams, deep, short spandrel. If the beams are flexible, then the moment of inertia will be close to this independent shear walls. If the beams are rigid, then it will be like this. Then there is another additional advantage of these coupling beams. These coupling beams are going to yield before yielding of the shear walls, and these will dissipate a lot of energy. So these the energy dissipation capacity of the shear wall increases by providing coupling beams. And that's why the response reduction factor, which is allowed in case of coupled shear walls, can be larger than what we are allowing in case of cantilever shear wall, because more energy dissipation takes place here. But these coupling beams, which are subjected to very large shear force, these needs special detailing. Now, in a shear wall, coupled shear wall, we can consider that the vertical shear walls are like columns, and these beams are connecting these wide columns. And any section of these columns, including the one which is connecting with these beams, this will remain rigid, plain, and perpendicular to the neutral axis after bending. So when the shear wall will be subjected to lateral load and it is bending, so we can see that this section here, which was perpendicular to the original axis of the shear wall, will be perpendicular to this new axis of the shear wall. And this coupling beam will be subjected to very large shear deformations. And as a result, its concrete may get crushed. And the truss analogy which we are using for shear transfer in our normal beams may not be applicable here. So first of all, these beams are going to damage. Hinges will form in these coupling beams because these are subjected to very large shear deformations as shown in the left side figure. And then the shear wall will start yielding here at the base. And due to reversible nature of earthquake, the tension will occur on one face, and then when the earthquake reverses its direction, the tension will occur on the other face. So first, the energy dissipation takes place in the coupling beams, and then finally the hinges will form at the base of the shear wall, and these will also dissipate energy. So in case of coupled shear walls, when we have openings due to functional requirement, doors and windows, due to these openings, it looks like that we have two shear walls which have been interconnected by these coupling beams, and the mode of resistance of lateral load by flexural action of the individual walls and framing action is occurring because of the coupling beams. And the coupling ratio, this is the ratio of the moment resisted by frame action or the coupling beams to the total overturning moment. So if CR is equal to 0, so there are no coupling beams, and if CR is equal to 1, then 100% transfer. That means it is acting as the two shear walls jointed together. In that case, the moment of inertia will increase 4 times. Then if the shear stress in these beams, coupling beams, is increasing, is more than this value, then we have to provide diagonal reinforcement, because as I said that the coupling beams will be subjected to very large shear force, and the concrete may get crushed, and when the concrete gets crushed, the shear transfer through truss analogy cannot take place, and in that case we have to provide reinforcement, and the diagonal reinforcement will resist the moment as well as the shear force. So this formula we can understand from here. So this is shown only symmetric half of the coupling beam. Actually, similar coupling beam is continuing. So here a hinge will form, a flexural hinge will form at the center, and here pure shear will be acting. And this shear will cause a shear force here and bending moment. So this diagonal reinforcement has to resist the shear force as well as the bending moment. So vertical component of this reinforcement, diagonal reinforcement, will resist the shear force, and the horizontal reinforcement will resist the bending moment. So we can calculate the amount of the reinforcement required from the bending point of view and also from the shear point of view. Now, this diagonal reinforcement which is to be provided, it is to be provided in the form of bundles here, these diagonal bundles, and this bundle is to be provided with special confining reinforcement, similar to what we are providing in the columns. Similar confining reinforcement is to be provided. So if we look at the reinforcement detail, this is the boundary element of the shear wall, and this is our diagonal reinforcement bundle. And two types of detailing are possible. One is that we provide confining reinforcement along on this bundle of diagonal reinforcement, but that may be a bit complex to provide. So another possibility is that we provide confining reinforcement in the full of the coupling beam itself. So these are shown in ACI 318 with these diagrams. So here special confining reinforcement is provided along the diagonal reinforcement. Around the diagonal reinforcement, special confining reinforcement is provided. But in this case, the special confining reinforcement is provided in the beams itself. Here, along the bundles, nominal reinforcement to keep them in place will be provided. And in section, it will look like this. This is the diagonal reinforcement, which is appearing at the section, and the special confining reinforcement is provided over the whole coupling beam. Now, in real practice, it will look something like this. So here you can see that special confining reinforcement is provided on the bundles, but it appears to be quite complex. How to provide that reinforcement here? It is not easy. The other possible detailing is this, where special confining reinforcement is provided in the coupling beam, and in addition to that, you can see that the diagonal reinforcement is provided here. And this diagonal reinforcement should continue into the shear wall. As per ACI 318, this anchorage has to be LD, and as per our code, this anchorage has to be 1.5 times LD, the development length intention. Then this design, many times depending upon the amount of shear stress we are getting, can be very complex. So different types of detailing are provided. One is that we do not provide diagonal reinforcement if the shear stress is limited or the slenderness ratio of the beam is higher. So this diagram explains that in which range of stress and slenderness ratio, which type of detailing is to be provided. So on x-axis, we have beam span to depth ratio. It's written height, so depth of the beam, it is here. So 1 to 6 is shown, and if this ratio is more than 4, then this can be detailed like the beam in case of a special moment adjusting frame. So whatever detailing we do near the joint, same type of detailing can be done here. On the other hand, if it is less than 2, then we require diagonal reinforcement. So in case of span to depth ratio is less than 2, and then the shear stress is also higher. So shear force divided by the shear capacity ratio, ACW square root FC dash. So ACW is the area of the web, and square root FC dash is proportional, or the shear strength is proportional to square root FC dash. So if this ratio we take, so this ratio, if it is more than 4, then the diagonal reinforcement is required. In between, it is the choice of the designer whether he wants to provide diagonal reinforcement or want to detail it as a special frame beam. Then in many cases, people are using composite or metallic coupling beams, because I told you that contrary to concrete, steel is very ductile in shear. So shear is a problem in RCC, but it is an advantage in case of steel. So if we provide a steel plate or a steel section here, that section can not only resist shear force, it will also provide ductility due to the shear. And smaller the span, more will be the ductility. So because shear is more ductile in case of steel than flexion. So here a short beam is not a problem, rather it is an advantage. Only thing is that this beam needs to be properly anchored into the boundary zone. So boundary chain is already having congested reinforcement. So this is shown here, the boundary element of the shear wall, which is having closely spaced longitudinal reinforcement as well as stirrups and ties. So those stirrups and ties have to be continued through this. So these holes are to be provided through this. These have to continue, because otherwise, if we discontinue these ties or stirrups here, then the boundary element will be unconfined, and that will become the weak point. And second issue is that this anchorage length of this steel element into the shear wall, this needs to be sufficient, because when it will be subjected to double curvature banding, it will be applying very large bearing stresses into the concrete, and the concrete adjacent to this element here, or here may get crushed. So that needs to be avoided. So this is detailing a typical photo I have taken from the net, where special confining reinforcement along with this steel coupling beams is shown here. Sometimes people are also using especially designed elements here. These elements are designed in such a way that these are acting as fuse. Their strength is intentionally kept on lower side, so that during the earthquake, these are yielding first and these are dissipating the energy. And even if these get destroyed after the earthquake, these can be simply removed from these bolts and replaced. So this is another concept, and it has been done practically also. Now, this length, embedment length of the coupling beam, steel coupling beam, into the shear wall, this is the crucial issue. So it can be assumed that there is a point of contraflexion in the middle of this coupling beam, because this will be bending in double curvature, and whatever is its shear capacity. So this BU is the shear capacity of this coupling beam, steel coupling beam. So that shear capacity, that much shear force will be developing here. And due to that, there will be a bending occurring inside the shear wall. And due to this bending, a rotation will occur about some point here, and the strain will vary like this in a straight line fashion. And the strain, maximum strain, which can occur here before crushing, is 0.003. So the maximum crushing strain which can be permitted here. So corresponding to this strain, we can calculate the stress block. Al Tawil, they have done a lot of study on that, and a design method is provided. Still, this design method is not accepted or not incorporated in any code, but so far this is the only method through which we can design these metal or steel coupling beams. So the strain variation is assumed to be linear, and it will be compression on this side and compression on this side. A rectangular stress block of 1/3 the length, embedded length, LE is the embedded length. So 1/3 of that embedded length can be assumed here, and its resultant can be calculated. And then here the parabolic strain variation, depending upon how much strain we are getting here, we can calculate that strain based on this point of rotation, and we can calculate the stress block here. And then this compressive force vertically downward, this we can also get. Difference of this and this in the upward direction, that will be equal to VU. So this VU we can obtain from equilibrium. So this force acting upward and this force acting downward, difference of these two will be equated with this. And this lever arm, which will form a couple, or not exactly couple, this will provide an eccentricity, and equilibrium of moment about any point should be satisfied. So we can take moment about this point where this downward compressive force is acting, and then we can satisfy the moment. So there are two unknowns, and those two unknowns are, one is this LE, and another is this point of rotation. So these two unknowns can be obtained using these two equations. One, equilibrium of the force, that is equal to V, and another is the equilibrium of the moment. And we have to iteratively modify this LE in such a way that the stresses here are within the permissible limits, whatever is permitted in the concrete. So that much. 0.67 FCK in our case. It is 0.85 FC dash for the cylinder. We are using cube strength FCK, so it will be 0.67. So this stress should not exceed 0.67 FCK. So this embedment length needs some care in calculation, and then the detailing of the confining reinforcement in the boundary elements. One way I explained was that we can provide holes into this steel element through which our stirrups can pass. Another possibility is that we can weld this reinforcement to the valve of this steel element. We can weld so that the confinement is available. Then in some situations when the opening is very close to the one edge of the shear wall, it forms a small portion of the shear wall which we call edge pier. So this edge pier, a small portion of the shear wall, this, as I told, that the pier will be bending in double curvature, and it transfers a lot of shear from the upper portion of the shear wall to the bottom portion of the shear wall. And this will be transferred to this edge pier through this horizontal reinforcement at top and also this horizontal reinforcement at the bottom. So when the force is transferred from the upper portion of the wall to the edge pier, then this reinforcement is required. And this reinforcement should be adequate to transfer that shear capacity of this shear wall, this end pier, into the shear wall. Similarly, in the bottom portion also, this reinforcement should be adequate to transfer the shear force developing here into the remaining shear wall. And it needs to be anchored sufficiently into the shear wall so that this reinforcement does not slip. So a special type of detailing is required. Additional horizontal reinforcement is required at the top and bottom of the edge pier when the pier size or pier length is much smaller as compared to the rest of the shear wall. So thank you. These were the points which I wanted to discuss, and we can take up the questions.
Thank you, sir, for the excellent presentation. Definitely, as discussed in the morning, the practicing engineers will be having tough time, at least in initial stages, to do this minimum thickness and overstrain factor. So we'll take the questions. First question is, for stability of tower, ground embedment of 15% is recommended in 16700. Are there any other provisions included in revised 1893 with raft and pile raft, especially pile raft?
Regarding tall buildings, these codes are not giving any provision. So tall building design will remain to be governed. So or the clauses, specific clauses which are related to the tower and podium, those will be there in 16700. So these codes are for general buildings. So I cannot say that these are not applicable to tall buildings. These will be applicable to tall buildings also. But the specific requirements of the tall buildings will not be covered. So that clause we have to continue to follow. So that much is required.
Thank you. Next question is related to IS 456. Means, are the provisions in the expected revised IS 456 will be also in integration with these codes?
Yes. So this code will be in tune with the revised IS 456.
Next is the closed loop of wall shown in boundary zone is not supported by vertical bars. This needs to be a loop, but can be just LD, I guess. That you have explained afterwards, I think. Yeah, already. The loop, a whole closed loop in the boundary zone. What What care to be taken for shear walls of 6 meter length and thickness of 230 mm? Similar questions are there. The shear wall of size 250 mm, will it be valid? Or that's what I was telling. The practicing people will have definitely issues as far as the practice. But those will be in initial stages. Finally, people will
Yeah,
reconcile.
slowly people will
Yeah, correct.
start understanding and interpreting these clauses.
Mm.
But what I'm saying that we should not feel that our revised code is too much.
Mm.
In case of shear wall, we are still lagging behind. And whenever this code will be revised, we should be ready for more clauses because international practice and understanding is much better.
Similar, all the further questions are almost similar to that. Mm. One is what will the cover if boundary elements are provided? As per the sketch shown, clear cover may not be maintained. Please confirm because as per the
No, minimum
columns.
cover is to be maintained. Whatever is required from the durability, that is to be maintained from
Okay.
the outermost rebar.
Mm. One is like in Ahmedabad high-rise buildings, damage for the earthquake happening at about 200 250 kilometers away. He was referring mostly to Bhuj earthquake. Why the issue of risk to long period effects are not part of code?
Risk to long period. Okay, so perhaps what he means is that due to local site effects, there may be long period amplification.
Actually, you
Uh,
covered it in the morning.
yeah, which we
Yeah.
discussed in the morning.
Yeah.
So that is possible, but no detailed study has been done in Ahmedabad. And one issue is that we do not have the records. So what actually happened in Ahmedabad, it is very difficult to say what was the predominant frequency. But in Ahmedabad, there was another big issue that our buildings were under design.
Mm.
So we can't say whether those failed because of their under design or they failed because the demand was much higher because of amplification of long.
Next is 2% drift for a larger return period earthquake MC is applicable or not?
I mean, now whatever is the design earthquake for that, the 2%. Okay, 2%.
2% drift.
Okay, okay, I got it. So there is a confusion regarding that 2%. Actually, 2% and 0.4% given in our code are same.
Okay.
The reason is that 2% is at the ultimate. That is the ultimate uh, drift. So that is multiplied by R.
R equal to 1. Yeah.
If you multiply 0.4 by R of 5, it is the same. So
Hmm.
don't think that some codes or American code or they are allowing 2% and our code is allowing only 0.4%. So can we use 2%? Our 0.4% is same as 2%. It translates to 2%.
Next is in shear wall at middle zone, if the percentage of reinforcement is less than 1%, still links are to be provided or not?
Yes, links are to be provided in the middle zone.
Hmm.
And in the middle zone, reinforcement will be less than 1% or 0.8% because that is required only in the boundary element. In the shear wall area, there is a separate table given in IS 13920 and it is roughly equal to 0.25%.
Thank you. Then can shear walls have pin support if they are designed as special shear wall to carry lateral force?
Then it will not be shear wall. Then it
Correct.
cannot act as cantilever. The shear wall will not be of much use. A shear wall which is pinned. So in case of shear wall, the advantage of the shear wall is that it is attracting all the lateral force and transferring it to the ground. And if it is not able to transfer to the ground, so then it will not act as shear wall. It won't be shear wall.
Okay. Next is column overstrength factor is to check axial load only or column or combined effect of axial and bending.
So I believe that will be for checking Axial force, bending moment, interaction, and shear.
Yeah.
Once the final code is available, then it will be clearer that whether it is only to check the shear capacity or it is also to check the axial force, bending moment, interaction.
So one doubt is that overstrength factor will lead to more steel. Then composite buildings in India will be more cost-effective options, or is it like that? I don't think so.
I don't think so, that because in both, whether it is composite or RCC or steel, we have to follow these overstrength factors, same overstrength.
So one is a basic question. If a multi-story building is idealized as a single degree of freedom system, then if the entire mass is dumped at the top of roof, instead of CG along the height, then the BM and shear force may increase. Hence, limiting the height of single degree of freedom system, lumping of mass at vertical CG may give some same bending moment shear force. Will this
No,
cause any disturbance to mode shapes, etc.?
of course. So, single degree freedom system cannot
Yeah.
simulate. We have to consider multi-degree freedom system, and that will affect period and mode shape force. So, it is to be analyzed at multi-degree.
And it's a perennial question. Using a floating column in tall building is safe or not?
The question perhaps is that can we use floating column or not? So
Yeah.
you can use floating column. You can design for floating column. Make sure that there it is not a strong column, weak beam. Here it is a strong
Beam, weak
transfer
beam.
girder and
Yeah.
weaker column. So the transfer girder on which your floating column is there, the transfer girder should be stronger. Their hinge should not fall.
Yeah. Same question in the morning. Can we follow diagonal reinforcement coupling means, or can it is required in case wind combinations are governing? So that has been already answered in the
So it will
morning.
depend upon what is the stress level under earthquake. So under design earthquake, if the stress level is more than that formula which is given, then we have to go for diagonal, irrespective of what is in wind. So wind may be governing. So whatever size we are get, so if we are getting the stress within that limit, if the size due to wind is such that stress comes out to be less than that, then diagonal reinforcement is not needed. But if the stress is still exceeding that limit, then we have to provide diagonal.
Thank you. Next is, will coupled shear walls with coupling mills have less displacement when compared with single shear wall? Maybe of
Yes, of
equivalent
course.
stiffness.
Stiffness increases when we are coupling the shear wall. And now, when you say single shear wall, then which single shear wall?
Must
What will
be
be the length?
equivalent
If the
thickness.
length is equal to the total length,
Yeah.
then no.
No.
If the length is equal to the individual shear walls, then yes.
Then this overstrength in is to be checked in coupling designed for coupling mills or also or not.
Okay, this question was raised. I think you forwarded me those
Yeah.
details,
Yeah.
New Zealand code. So
Yeah.
it is interesting. So actually, it is reverse way. The question, what I got, the impression from the question was that when we are designing coupling beams, do we have to consider overstrength factor? It's other way around. That when we are designing the shear wall should be stronger than the coupling beam. Coupling beam should yield first. So what in New Zealand code they are explaining is that the coupling beam strength which we are calculating and actually we are providing is higher. Why it is higher? Because there is slab also. And in slab we are having reinforcement that act as a flange. So the actual capacity of the coupling beam is larger than what we are computing using rectangular section. So that should be taken into account as per New Zealand code. Our code does not specifically say that, but it is providing an overstrength factor of 3 for the shear wall. Hopefully that will take care of this also.
Thank you. Similar question, overstrength for foundation design in draft 456 and 1893 is different. but conditions in which overstrength factor for foundation is to be used is mentioned in ASC 7, which is missing in draft code.
Our new code, this 13920 part 5, it is saying this overstrength factor of 3 is to be used for foundation also. When we are designing the raft foundation for shear wall, the raft foundation is to be designed with this overstrength factor of 3. So that will take care of.
Thank you. Next is, will it be required to have thickness of shear wall 23 times the diameter if the beam is released in the perpendicular direction?
Well, if you can really release it, then it can be done. But practically, it is not possible to release. I mean, we have to follow some special detailing.
Yeah.
Release not only in the model, it is to be released in construction. So you have to come out with some type of detailing in which release is provided without slip of the reinforcement. So reinforcement is not allowed to slip.
Maybe in secondary beams, if you provide very less top reinforcement, in secondary, not frame beams, what about second?
Two situations we have to consider. One situation is that suppose the reinforcement gets fractured. Then if longitudinal reinforcement gets fractured, then it should not fail in shear. Second is that if some people, they provide inadequate development length, so the reinforcement slips. So if reinforcement slips, longitudinal reinforcement slips, the beam is prone to failure in shear. So we have to take care of that. Some special type of reinforcement detailing we have to provide so that the moment is not transferred, but at the same time shear continues to be transferred. So if we can do that, then this is okay.
Next is, transfer girder should be designed with overstrength factor even if the floating column it supports is not part of LLRS?
Yeah, still.
Yeah.
Because even if you are not taking its advantage in resisting lateral load, but if its capacity is more than the beam, then in any case it will fail the beam. And once the beam fail at the mid point and hinges form at the ends, it will become a mechanism and it will collapse.
Next, I have not understood this, but can we allow the pressurized shaft cutout in boundary element?
I am also not able to do that. Pressurized cutouts.
Yeah, I have not understood that. With reference respect to the equivalent single shear wall matching the overall length of the coupled shear walls and coupling, that was the answer to earlier question. Equivalent means total.
So in case the wall length is equal to the total length of the coupled shear wall and you are providing a solid wall of that length, definitely that will be more stronger and stiffer.
Yeah. That's all I think till now. We have completed the questions. Anand, you want to ask anything? Or anybody from the panel?
No, I don't have any question.
Yeah. Okay. Then over to Rashmi. We are ahead of time today.
Yes. First time it has happened that my presentation has been finished. Otherwise, I was always having some slides remaining.
For a change.
Thank you so much for your great presentation. And I hope every participant and panelist or professional must have gained some knowledge about your expertise. Thank you, Lakshmi ma'am, for the same.
Thank you.
I would like to introduce our one of the director, Deshpande sir. He will be presenting the vote of thanks for the presentation. So Ravindra Deshpande sir is an MTech structure in 1981 and BE Civil in 1976 from BJTI. He is associated with Epicons since 1985. He serves as a director and as a part of top management of the company. He is in charge of Structural Design Unit 3 and being operated from our Dadar and Dairy office. His expertise include evolving a strong and most efficient structural engineer for a given building and optimizing the structural design within the frame of IS regulations. His unit has won the award of Best RCC Structure of Uttarakhand for ONGC Corporate Office at Dehradun, offered by ICI and Ultratech. He is a member of various organizations such as Institute of Engineers, Indian Society of Structural Engineers, and Indian Concrete Institute. So, welcome Deshpande sir, the panelist, and over to you. Thank you, sir.
Thank you. So, friends, good evening. So we have come to the end of the webinar, which had 4 elaborate sessions throughout the day, for which I would like to thank the speakers, Dr. Yogendra Singh and Dr. Lakshmi, for their enlightening presentations. I am sure these sessions will provide a very useful knowledge to the participants, which will be useful for them in their regular practice. I would also like to thank the participants who have joined from all parts of India, including remote states in north like Jammu and Kashmir down to Kerala and Gujarat to West Bengal. The credit for such a large participation, firstly, I think goes to the subject itself, combining the wind and seismic forces. As we know, when we check the structure for its strength, serviceability, and stability, sometimes a particular case governs the strength, but the other load combination governs the serviceability. So the importance to both the lateral force systems should be given, and this has been done successfully in today's webinar. I also give the credit to the popularity of the learned speakers. So with that, I also thank the wide angle forum led by Priya Gokhale and admin staff of Epicons for making this webinar a success. With this, I conclude my vote of thanks and declare the webinar is over.
Thank you.
Thank you.
So we call it a day. Thank you.
Thank you, everybody.
Thank you everybody for joining.
Yeah.
Thank you.
Bye bye. Take care.
Yeah.